Hello friends, welcome again to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss the excited states present in the diatomic molecules, and then we will see the types of the transitions which may be there in your diatomic molecules. Okay, and then we'll check the conditions, which transitions are allowed and which transitions are not allowed. Okay, so before going into the details of the today's lecture, let us recollect what we have done so far in the last two lectures. Okay, so if I go back, right, so I have started from here actually, and I already told you these, see, when you do this, when you calculate the molecular term symbols for your molecules, right? So why it is necessary actually to determine, not calculate, to determine the uh, molecular term symbols. As I already told you, these diatomic molecules generally have the very large number of the excited states. Okay, so and each excited state is generally recognized by its own term symbol. Okay, this concept actually I have told you, and today we will see the importance of these term symbols for the different excited states and how we can recognize that certain transitions are allowed and while certain are not allowed, depending upon the different types of the rules, right, which are there to actually decide the molecular transitions, allowed or the forbidden molecular transitions. Okay, so see, if you have seen the last two lectures, then it would be very easy for you to understand. But if you are new here and watching this particular video for the first time, it's my suggestion to you, please watch previous two lectures actually, right, which is given in the playlist of molecular term symbols in the tetrahedron chemistry classes. Okay, so this was the situation, and then I have given you the rules. Okay, and based on the rules, then I have calculated, sorry, I have determined the molecular term symbols for the different species. Okay, and these are all the things actually which I have explained. These are the molecular orbital diagrams which are must to actually designate the term symbols for any ground state or the excited state. Okay, this was the situation. This much of things I have discussed in the first lecture, and then in the second lecture I have explained all these things, like your heteronuclear diatomic molecules for also I have calculated these molecular term symbols. Okay, this was the case of your carbon monoxide, and this was the CSIR net problem which I have discussed. Okay, and now in the today's class, excited states and the transitions in the diatomic molecules. Okay, as I already told you, these may have the very large number of the excited state. So let us go back actually to think to check the excited states of the molecules. Okay, guys. So this you have been given that this carbonyl, right? This is CO, and this CO is having this particular molecular term symbol which you are watching here, which I have explained in the last term, in the last turn actually, right? So what can happen if you have the excited state of this carbonyl? Okay, so there may be the large number of the excited states, but I am going to discuss only one or two excited states, only one excited state for this one, and depending upon the electronic configuration given in the question, you can actually determine the excited state. Okay, so let us remove all these things. Okay, let us remove all these things, and now we'll see how we can go for the excited state. So I'm writing CO and putting a star over there, which simply means it is the excited state, and there may be the possibility of the two kinds of the excited state. So the first possibility of the excited state is just like that. Your electron, right, your one of the electrons which is present on the sigma anti-bonding molecular orbital, it may jump either to this 2px orbital or to the 2py orbital. Okay, this can happen actually. So what I am doing actually, I am promoting this one electron from the anti-bonding molecular orbital sigma to the this 2px orbital. Okay, I am doing this one. So this would be the first case. So if I draw the electronic configuration now, what will happen? This will have only one electron now. Okay, and one I have promoted to this 2px orbital with the parallel spin, right? This is the excited state configuration. So if you write the configuration for this one, so how you can write, this would be sigma 2s anti-bonding. Now this will carry only one electron, and obviously its energy is less, and then you are having pi 2px antibonding molecular orbital, and in this you are also having one electron, and this would be equal to that pi 2py antibonding, and this is having no electron, okay, because I have promoted only one electron, so this 2py would remain empty. So now if you want to calculate the term symbols for this one, for this actually there is no orbital angular momentum, so for this you will put 0. This I have explained in my previous lectures also. And since this because this sigma orbitals are actually non-degenerate, while rest your pi, delta and phi, they are the doubly degenerate. So it is the doubly degenerate, and if you calculate the orbital angular momentum for this one, so this px can have +1 value and this can have the -1 value. However, it is difficult to designate which one is the +1 and which one is the -1. Okay, so this is the configuration. Now I am determining the term symbol for this excited state. So number one, determination of this quantum number, that means delta determination. Okay, this I have already told you, this is a net orbital angular momentum. Okay, and for this see uh, this sigma antibonding is having one electron and the value for this is 0. So what you will do, you will write 0 for this one. This is your m1 value, rather you can say this is your m1 value. Then plus your next electron is present in the pi, and pi 2px antibonding, so it will have the value of the +1. So what you will do, you will write the +1 here, say this is your m2. If you couple them, right, and then you will have the net value of the 1. And when this value is 1, it simply means your spectroscopic term for this would be pi. Okay, this I already told you. If you recollect, actually, if lambda is 0, then it would be your sigma, and if your lambda is 1, then this would be pi. If it is 2, then it is your delta, and if it is 3, then it is phi, and so on. Okay, so for 1 it would be actually pi, so I have written pi here. Okay, there is no problem in that. Now in the second case, you will determine the spin multiplicity, so that would be 2s plus 1, and this would give you that means 2 multiplied by the spin of these two electrons. So this will have plus half, this will also have plus half. You see, both have the parallel spins, right? So this will also have the plus half, and this will also have the plus half value. So this plus half and plus half, it will make 1, 2s plus 1, that will give you 3. So it means spin multiplicity is 3. So the term symbol would become, so I can write term symbol. So that term symbol would be pi, and there is the spin multiplicity. Since it is a heteronuclear diatomic molecule, so there is no need to put the G-rayed or un-G-rayed, because they are not having these heteronuclear diatomic molecules are not having the center of symmetry, and since this is a pi term, so there is no need to put the sign of the wave function with respect to the sigma v. So this is the case when you have promoted one electron from here to here. So I hope you have noted down this thing. Now you may have another situation, then say you may have another situation. Let us check that situation also. So what I am doing, I am removing all these things. I don't want all these. I hope you have noted down, or you have taken the screenshot of this. Okay, now I am removing all these things. Now what I am doing, I am promoting one of the electron from here to this px actually, and now I am giving the inverted spin to it. Okay, this is another excited state possible. So like this, you may have the large number of the excited state for which you can determine the your term symbols, molecular term symbols. Okay, so for this again I am doing the same. First case I am determining, in the first case I am determining your lambda. Okay, so that lambda would be equals to 0 plus 1. Again it will give you the 1. When lambda value is 1, it simply means this term symbol would be the pi, and if you calculate the spin multiplicity 2s plus 1, that will give you 2 multiplied by plus half minus half. Okay, why plus half minus half? Because this is having the plus half spin and this one is having minus half spin, because it is anti-clockwise, it is clockwise. Okay, and if you solve this value, right, then plus 1 you will write. Okay, then that will give you the 1. So your term symbol would be pi 1 in that case. Okay, so if you want to know the energy order for this one, so you will get 3 pi would have the lower energy and this will have the higher energy. And you know, ground state, you are already having that ground state electronic molecular term symbol, that was your 1, that's positive. Okay, so this is the energy order of the different term symbols for the ground state as well as for the excited state. I hope this makes the sense and you understood the thing. Now let us check one more thing. Go back. If I go back, what is the, oh, so if this is your HF molecule, and if you want to determine the molecular term symbol for the HF molecule, so it's my request to please note down the molecular term symbol of normal HF, right? That means it is in the ground state, then it is having the molecular term symbol of sigma 1 positive. Okay, I'm removing all these things. Okay, fine, I have removed all these things. And now what I am doing, I am promoting the electron. So how I can promote the electron? So what I am doing, one of the electron which are present in this non-bonding set, so this is your non-bonding set, I am going to promote one of the electron from here to at the top position. Okay, so the configuration would become just like that. Right, only one electron it is having. Okay, and I have promoted one electron from here to here, and I am giving giving the same spin actually for this one. Okay, so spin for this one is plus half and for this is also plus half. Okay, when this happens actually, then you can go for the excited state configuration. So I am writing here HF excited state. So I am putting a star for this excited state. Okay, and configuration would become just like that: sigma 1, which is having the 2 electrons having lower energy, then your sigma 2, it is also having the 2 electrons, then another lower energy, and then you will have your non-bonding electrons, that is Nb, and it would be the pi type. And from here now you will have only 3 electrons, right? You see 1, 2 and 3 electrons, and then you have promoted 1 electron from here to your sigma anti-bonding, which is of sp type. Okay, and you are having 1 electron over there. Okay, so you know your last electron is in the s orbital. Basically it is sp hybridized, but it is considered as the s orbital. So for this actually the value of your orbital angular momentum would be 0. Okay, this you should remember. And for this one, if I draw the configuration just like that, so this was having 2 electrons. Okay, and it is having the plus 1, and it is having the value of the minus 1, having 1 electron only. So this is the configuration of this. Okay, now if you want to calculate first thing, that is that quantum number, net orbital angular momentum, that is lambda, that would be plus 1 plus 1 minus 1 plus 0, that will give you the 1. So how it has happened, it had happened actually, you see, plus 1 I have put it for this electron, that means for this electron. Then next plus 1 I have put it for this electron, because both having the plus 1, this pi actually orbital is having the plus 1 value, and this one is having the minus 1, and this is the 0. This will give you the value of 1. And you know, when your lambda is 1, simply you will have your pi symbol. Okay, now if you go for the spin multiplicity, 2s plus 1, that will give you 2. Okay, multiplied by plus half, because both are having the same spin of the plus half. So if you write +1 here, that will give you the 3. Okay, then what would be your term symbol? Term symbol would be 3 pi for this excited state. So see how easy is this to actually determine the molecular term symbols for the excited states. I hope this thing is now quite clear to you. Now I am going to explain you another thing. Let us check what I have. So this we have done, this we have done, this I have already explained to you. Now you can see this here, if this is quite clear to you. So these are the three different forms of the oxygen. So this is the molecular or the orbital diagram for this one, right? This is for oxygen actually, right here. And let us check which one is for oxygen. Sorry, this one is for oxygen molecule. The extreme, what I am doing, I can write here. This is for O2 molecule. Okay, and after that you are having this O2 triplet. This is O2 triplet, and this one is for O2 singlet. So this oxygen molecule can have various excited states, and the most important excited states are the singlet and the triplet state. So in the triplet state, basically you will have the two unpaired electron. It is paramagnetic, right? If you do the electron spin resonance spectroscopy for this one, then you will get the signal. And here you see in the singlet state, both electrons are paired. And how actually these names singlet and triplets are given to you, I have already explained in my some of the previous lectures actually, right? You can see I have explained this term various times, but I'm not going to discuss that thing again, because my aim to determine the molecular term symbols for these states, right? So these diagram actually you should remember, you should memorize actually, right? So see, for molecular oxygen, I have already done in the last lecture how actually you determine the molecular term symbol for this one. So I'm not going to actually determine the molecular term symbol for this one. So basically it is not quite clear here, so I can write here. This is actually your 3 sigma G rate with negative sign. Okay, so this was the case. You can determine by using the rule, but I am more focused on your excited state. So first of all, I am going to discuss the molecular term symbol for this your singlet state. Okay, so in singlet state, if you determine that value of the lambda, so what it will give you, it will give you +1 and +1. That will give you the 2. Okay, this is something very important. Okay, because you see your electrons are having, both electrons are in this orbital actually. Okay, in this orbital, and it is actually p orbital, right? And then if you go for your say spin multi, see, if it is 2, right? If it is 2, it simply means, that mean you will use lambda. Okay, sorry, delta, not lambda, very sorry, it is delta. This was the first case. In the second case, if you want to determine the spin multiplicity, that will give you the 2s plus 1, so that is 2. And you see here both electrons are paired, plus half and the minus half. So what you can do, multiply it by plus half minus half plus 1, that will give you the 1. 2s plus 1 is 0, right? Just like that. And after that you can determine the parity, because this oxygen molecule is homonuclear diatomic molecules. So you have to decide whether you will put G or U as the subscript along with your delta. So how you can determine the subscript, you see here, because you see this actually this orbital where you are having this electron actually, right? This is G rate actually, right? So you can put 1 G for the first electron, second G for another electron. Okay, so it will give you G multiplied by G, that is equals to G. Okay, when it is G, then in that case you can write delta G1. So this is the molecular term symbol. Okay, and I hope this is clear to you, which I have explained here. So there is no need to put sign plus or minus, because plus and minus sign we put only for your term, spectroscopic term sigma. Okay, this is important. Oh, I hope this is clear to you. Okay, 1 delta G. Now I can explain the second thing, which is your triplet state. So I'm going for your triplet state. So how you can determine for this triplet state? Again, it is quite easy. Go for the delta, that will give you the plus 1 and minus 1. Okay, and you know why it is plus 1 and the minus 1? This I hope you know. See, for this you will have the value of the plus 1, and for this you will have the value of the minus 1, while in the earlier case for both you were having the plus 1, that's why you got the value of the 2. Okay, so plus 1 and the minus 1, and if you subtract this will give you the value of the 0, and when it is 0, then the ground state the spectroscopic term would be the sigma, and then you will go for the spin multiplicity, that is 2s plus 1, because both electrons you can see here in that case, however they are present in the different orbitals, but their spins are inverted. Okay, their spins are inverted. So you can write 2 multiplied by plus half minus half plus 1 equals to 1, and if you go for the parity, so again you see this is pi anti-bonding. Pi anti-bonding is always G rate. So this is G rate, this is also G rate, and earlier this was also the G rate because this was the pi anti-bonding. So if you put here the value, that is G multiplied by G, that will give you the G. Okay, and since you know this term is the sigma term, now it is essential to put the positive or the negative sign, right, for to know the sign of the wave function with respect to the sigma plane, that is sigma v. Okay, and since the trick is that whenever you have this value 2s plus 1 equal to 1, right, so you will put the plus value, and remember one, right, you will put the plus value for this one, right, and it is again you see this is actually what sigma g, and whenever you have the sigma g you will always put the plus sign over there, which I have told you in my previous lectures. So the term symbol would become sigma g1 of plus. Okay, so this is how you can determine the things actually. Okay, I hope this much of exercise is quite sufficient to understand the energy of the ground state and the excited state term. Okay, so if you want to determine the ground state and the your excited state, the energy order for them, so I can go for this, that also. So for this I have to remove this. Okay, I have removed for this one, and now for this oxygen you are having three symbols, right? First you are having 3 sigma g negative, and then you are having, say, next is you are having delta g1, and then you are having 1 sigma g plus. Now you have to decide actually which will have the lower energy, which will have the higher energy. So remember, there are certain rules. The first rule says that if you are checking the rule number 1, if the value, you will check the value of the 2s plus 1, right? If this value is the highest, right, then your ground state term would belong to your ground state would be like that. It is when actually 2s plus 1 is having the higher value. So if you are comparing all these three, right, 1 2 and 3, so in that case the 2s plus 1 value is this one, right, so this will have the lowest energy in that case. That means this is the ground state. Okay, so you will straight away put this sign here. Now you see in the second step you are having the 2s plus 1, the value of the 2s plus 1 is 1. Again here the value of the 2s plus 1 is 1. So you cannot decide the energy of these two terms based on the spin multiplicity. When this happens actually, then you have to actually go for the value of the lambda, right? You have to decide the value of the lambda. Okay, so I am telling you, higher the value of the lambda, higher value of this lambda is having lower energy. It is having the lower energy, right? So if you want to check for this delta, actually the value is 2, and for this sigma the value is actually 0. Okay, so this value is higher, so this will have the lower energy, so you can put that sign. So this is the order actually. So this is the little trick to not trick actually, this is the method actually. However, you can understand these things rather quickly if you go for the group theoretical treatment, right? But in the simple case you can determine in that manner. First go for the spin multiplicity. Higher the spin multiplicity, lower would be the energy and it would be the ground state. And when the spin multiplicity is same, then you can check for the value of the net orbital angular momentum. Higher the value of the net angular momentum, lower would be the energy. So if you follow this, then you will find this one. Okay, so this is how you can determine the things actually, right? This is quite clear. And see, please wait, I made a mistake here. uh, this should be 1 sigma. Okay, this is 1 sigma g positive. Okay, fine. No, no mistake actually, right? So this is fine. Okay, so this is how you can determine. I hope this is clear to you. There is no problem in that. Okay, now this is the order of the energy, right? There is no problem in that. Now if you want to know the bond strength, order of the bond strength, so I can write it here. Order of bond strength, order of bond strength. So how you can go for the order of the bond strength? Whenever your electrons are present in the lower energy orbital, that means the bond strength would be very very high in that case. Okay, so if you see, if you compare the energy actually, right? So energy is actually lowest in this 3 sigma g, right? Energy is lower. That means its bond strength would be the highest one. So if you go for the bond strength, then you will write in that manner. Your 3 sigma g negative would have the highest bond strength. Okay, now if you want to compare the others actually, you can go for the similar energy order. Now second is this one, so you can write delta g 1, and this will have the lowest energy actually, right? So whatever the lowest bond strength, so whatever the energy order would be there for the ground state and the excited state, you reverse that order to get the bond strength. Okay, now you can go for the bond length also, order of the bond length. So I can write here bond length order. So how you can determine the bond length order? It simply means actually, see, this order may confuse you. Bond length. Okay. So what would be the order of the bond length actually, right? So whenever your bond is stronger, then it would be shorter, right? And whenever your bond is weak, then it would be longer. So this is something very very important which you should know actually. Okay, so generally excited state actually will have the weak bond. So excited state, whenever excited states are having the weak bond, definitely their bond length would be the higher. So ground state term would have the lowest bond length in that case, and ground state term, your this one. That is, if you go for uh, bond length order, so highest bond length would be for this excited state. Okay, followed by this, and lowest bond length would be for the ground state, that would be 3 sigma g negative. Okay, so now the important question is that, okay, this is fine that ground state term is the 3 sigma g, that means the bond is the strongest, that means the bond length would be the smallest one. Now how we can compare the two excited states, the bond length for the two excited states, right? So in that case, you see both electrons are paired in the same orbital. They are present in the same orbital. But in that case, where electrons are present in the different orbitals, right? And they are having this spin. Okay. So whenever this happens, then you will go for the second option. Please remember this point actually, right? So excited state, for the excited state term, you will look for the value of the delta. Higher the lambda, higher the value of the lambda. So in that case, your delta, if you go for the lambda for this one, it would be 2 actually. For this is 0 actually, right? So this higher value actually will belongs to the higher bond length. Please remember this one, right? So this is how you can understand. Okay, So let us check actually. Here I have also written here, higher value of the lambda is having the lower energy. Okay, please let me correct it. That means it is having the lower energy, right? When it is having the lower energy, it simply means okay, we cannot go in that manner. Actually, we cannot go in that manner. We simply actually solve this problem by using that energy relation. Okay, you actually, what you do actually, you invert the energy relation, okay, to get the bond length order, right? This is something very very important. Okay, and the next thing actually which is important, that means stretching frequency. Okay, now you can go for the another, that is the stretching frequency. I can use the different color for this one. Okay, bond stretching frequency, bond stretching frequency. Okay, so for bond stretching frequency, whenever your bond is strong, then you will require higher energy to stretch that particular bond. Okay, that means the stretching frequency actually is directly proportional to the energy. Okay, and for this actually, if you go for this reason, then this would be same for this bond order, right? So I'm writing here, bond order is directly proportional to stretching frequency. Stretching frequency. Okay, so this order and that order would remain the same. Okay, so this is how you can determine. So I hope this thing is quite clear to you. Now moving to the next one. Okay, next thing is the selection rules for the electronic transitions. Selection rules for electronic transitions. Selection rules for transitions. So this actually I have already told you in my coordination chemistry lecture, where I have determined the atomic term symbols. But let us recollect what we have learned so far. Say, first is actually the Laporte selection rule. Laporte selection rule. And what the Laporte selection rule says, that delta lambda, if it is equal to 0 or if it is equal to plus minus 1, then your transitions are allowed. Please remember. Okay, and then you may have your second point, spin selection rule. Spin selection rule. Then what spin selection rule says, that delta S, change in the spin multiplicity, would be equal to 0. When this happens, then it is allowed transitions. Okay, then you go for the number third, parity rule or parity selection rule or parity rule. Okay, so what it says, that this I have already told you, transition from gyrate to ungyrate and transition from ungyrate to gyrate are allowed. Okay, while gyrate to gyrate forbidden, gyrate to gyrate ungyrate to ungyrate forbidden. Okay, so ungyrate to ungyrate is also forbidden. Third rule. And last, that is number 4. I can write here number 4. What number 4 says, that if a transition is having from this sign of the wave function, if you have the wave function positive, obviously it would be there on the sigma term. Okay, and when this is happening from plus to plus, it is allowed, and it is happening from minus to minus sign. Okay, so we need to put this sign, right? So these are the allowed transitions, while uh, plus to minus is forbidden and minus to plus is also forbidden. So please keep in mind these rules. Okay, so if you have know this much of thing, then it is easy to determine or to know the kind of the your transitions, allowed or the forbidden transitions. Now let us look what I have. So this question I am having, and this question actually I have taken from CSIR net examination 2011. So it is CSIR net, okay, December 2011. Okay, so you have to determine the transition. So please remember first point, how to actually start the question. First of all, you focus on that thing which is which is actually clearly visible or clearly recognizing. So the important thing which I have already told you, the first thing which I have told you, check actually for this transition, G to U or U to G. This is easy, right? So we are checking this one. So this is G to G. G to G is actually the forbidden transition. So this cannot be your answer. You can strike out this one. A is not correct. Okay. And the second one is, again you see, rest all, in the rest all cases you see here, this is U to G, that means parity allowed. This is U to G, parity allowed. This is G to U, parity allowed. So I am writing here, okay, I'm writing for B. So for B actually, B is parity allowed, parity allowed. Okay, similarly your C is also parity allowed and your D is also parity allowed. So you have checked the parity. Now you know, you can check the value of the Laporte selection rule. Laporte selection rule, what it says, that you have to check for the delta lambda, right? So for the second transition, the value you see, actually I am going for the B actually, 0 minus 0, that will give you the 0. Okay, so if you go for the 0 minus 0, that means 0, and you know delta lambda equal to 0 is allowed. So how it is 0 actually? See, for this sigma term, the value of this lambda is 0, and here again in the excited state where the transition is happening, actually it is also 0. If you subtract, then you will get the 0. So B, C and D, they are actually Laporte allowed. They are also Laporte allowed. See, in that case, in the second case, right, if you go for the C, so I'm writing C here. So for C actually, transition is happening from your sigma zeros to delta 1. Okay, this is delta 1. So let us check actually whether it is delta 1 or not. See, this is 0, that means lambda equals to 0, then lambda equals to 1, then lambda equals to 2. So this is actually for sigma, and this is for your pi, and this is for your delta 2. But what the selection rule says, that this should be either this one, delta lambda equal to 0, or plus minus 1, but it is actually giving you the plus minus 2 here in that case. Okay, for C actually it is giving you the 0 minus 2, it is 2. That means C is not allowed. So you can strike out your C here. So your C is also, you can actually remove this C from here also, right? Now go for your pi and sigma. For if I am calculating for the D, so for D is actually what, this transition is happening from pi to sigma, so that is 0 minus 1, that is minus 1. So minus 1 is allowed, that means D is allowed. Okay, so D is allowed in that case. D, so far D is allowed, so far B is allowed. Now check actually the signs. Actually you see here, plus to plus allowed, and in that case you see there is no question of plus and minus here, so it could be allowed. So correct answer is actually, which is having the option B and your option D. So your option B is looking the correct, which is having two options. So you can mark this option B as the correct answer. So this is how actually you can you actually know how we actually determine the allowed and the forbidden transitions. Now moving to the next problem. Okay, this problem, the set of the allowed electronic transitions among the following. So this question actually I have taken from CSIR net June 2012. CSIR net June 2012. So how actually we can determine the transitions allowed or not? So let us check how we can do that. So here in that case, in the first one, here spin multiplicity is 4, here spin multiplicity is 2 for this one. So this cannot be allowed. Okay, since your Graded and ungraded is not there, then second easiest thing actually to know the spin multiplicity. Then moving to the next one, here it is 3, so it is spin allowed. It is 1, it is also spin allowed. It is 2, it is also spin allowed, but it is 3 to 3, so all are spin allowed. Okay, so B, C, D, E all are spin allowed. Now let us check another thing, whether they are allowed or not. So next thing is left with the sigma and pi. So if you go for the B, if you go for delta lambda, that will give you uh, sorry, this will give you 1 minus 0. How 1 minus 0? Lambda value for pi is 1, lambda value for sigma is 0, and that will give you the 1. Okay, and you know this is allowed. Okay, delta lambda equals to plus minus 1 is allowed. So it is looking like that your B is allowed. So you can mark this correct. Okay, now going for the C, again calculate the delta lambda. So what it says that, see, in that case, for this delta your lambda is 2, and for this delta also lambda is 2, so you can quickly write 2 minus 2, that will give you the 0. It is also allowed. Okay, so transition C is also allowed. Now go for the last one, that is the D. In the case of the D, transition is happening from pi to pi, that means 1 to 1 actually, right? So delta lambda, if you calculate, this will give you 1 minus 1, that will give you the 0. So this is B, C, D. This is D is also allowed. Okay, so you can write D is also allowed. Now go for the E actually, right? So I am going for the E. What E says, delta lambda, so 2 minus 0, that is 2. Okay, how? See, for this delta the value is 2, and for this sigma the value is 0. So this is 2, and you know delta lambda only 0 and plus minus 1 are allowed. So this is actually forbidden. So you can strike out this, you can strike out this. So correct answer actually B, C, D. So option C is looking correct. Option C. So B, C, D, option C is correct one. Okay, now moving to the next problem. Okay, the problem says that for an electronic configuration of the two non-equivalent pi electronic transitions, which of the following term is not possible? Okay, now this question is looking very nice, very important one, and this question actually I have taken from December 2013, CSIR net, December 2013. So how to solve such kind of the problem? Say I am doing for your, say, term symbol which are allowed, which is possible and which is not possible. So let us calculate very quickly. Let us calculate very quickly how we can go that actually. So first, in the first case, this is 1, this is 1, and both are having electrons in it, and you know for this value is plus 1, for this value is the minus 1. If you calculate that quantum number, that means plus 1 minus 1 equal to 0, and when it is 0 it is sigma. Okay, then you can go for the spin multiplicity, that is 2s plus 1. Both are actually the paired spin, that's 2 plus half plus half plus 1, that will give you the 3. Okay, so your term symbol would be 3 sigma. 3 sigma is there, yes it is. See, this 3 sigma is there, so B is possible, right? It is possible. Now you can go for another configuration, like let us actually draw the another configuration. So this I can give you the positive spin, this I can give you the negative spin. These are the possible transitions which I can put. This is plus 1, this is minus 1. If you calculate for the delta, that will give you the plus 1, and the minus 1, that will give you the 0, and that 0 would be your sigma. Now you can go for the 2s plus 1. So this will be 2 plus, sorry, not plus, it should be minus. it should be minus, no, multiplied, not minus, very sorry. So this is plus half, this is minus half, plus 1, that will give you the 1. Okay, so why actually I have taken this? Because this is having the plus half spin, this is having the minus half spin. So what is the term symbol which is possible for this one? Sigma 1. So this is also possible, 1 sigma is also possible. Okay, so this is also possible. Now going for the next one, what I can do actually, next thing which I can do, for this actually I have to remove this thing from here. So I am removing this one. Okay, now I'm going for the next configuration which is possible. See, this is pi and these are the another pi pair. So what you do, put one electron here and put another electron here, and you know for this value is plus 1, for this value is minus 1, and again for this it is plus 1, it is for minus 1. Okay, if you calculate the delta, then it would be plus 1 and plus 1, that will give you the 2. Why plus 1 plus 1? Because electrons are there in the plus 1, so that's why I have put it this. Okay, and when this value is the 2, it simply means you will have the value of the this one delta, right? Then you can go for the 2s plus 1, and in that case both have the paired spin. You see here, this is plus half, this is also plus half. Okay, and when this happens, both are the plus halves, then what you can do, you can simply write 2 multiplied by half plus 1, that is equals to 3. So term symbol would be delta 3. So delta 3 is also possible. So this is also possible. So you left with this one. Obviously D is not possible, so the correct option is the D. So how you can go for the D actually? Why this D is not possible in that case? Okay, D, why D is not possible? You know, you are having such things actually. Lambda equals to 1, 2, 3 and 4. Okay, and for this you are having the sigma, then pi, then delta and phi. Okay, and if you actually put the electrons right in those pi orbitals, you can never have that value of the 4. Okay, so this is the way, that means this D is actually is not the correct answer. Okay, now moving to the next problem. The first excited state of the hydrogen molecule is, so this actually example I have taken from a CSIR net, June 2016. Okay, so for this, what see, the first excited state of the hydrogen molecule is, so you should know actually the excited state of the hydrogen. So it's quite easy actually, guys. You see here, this is the molecular orbital diagram which you can draw for the hydrogen molecule. Okay, so this is your sigma 1s, you know it is G rate, and second one is your sigma anti-bonding 1s, which is un-G-rayed. Okay, and see, in the ground state actually you have both the electrons here, but in the question itself it is given that the first excited state. So for the excited state actually you have to remove one electron from here. So the moment you remove one electron from here and excite one electron with the parallel spin from here to here, so this is the configuration which you actually becomes sex like that. Okay, so and you know there is no net orbital angular momentum for the sigma orbital. So for this the value is the 0. So if you calculate this, that means 0 plus 0, that will give you the 0, and that will give you the value of the sigma. Okay, there is no problem in that. So if you want to calculate the spin multiplicity, that is 2s plus 1, that will give you the 2 multiplied by half plus 1, that will give you the 3. Okay, so far you are having sigma 3. So now go for the G rate of the un-G rate. So it is un-G rate actually, right? So your electron is present in the G rate, and your electron is present in the un-G rate. So how you can write actually the parity? First electron is in the G rate, second is the un-G rate, and multiplication of G rate and G rate will become actually the un-G rate. So you will quickly write U here actually. Now you need to put the positive and the negative sign. Since your electrons are there in the sigma orbital, you always put the positive. Okay, so see guys, please remember that point. You may have the confusion that this value is having the 3, so you will put the minus here. It is not like that. Whenever your electron is, this sigma term is coming from your sigma orbital, See, these are the sigma, this is sigma, and you are getting the sigma from here, then you will always put the positive here. Okay, so this 3 sigma positive U is the correct one, and this option is actually is the option D. So this is how you can actually solve the problem. Now moving to the next problem, what it says, the term symbol for the ground state of the boron. So boron, you know, boron molecule, see, boron is, if I write here, boron actually is having the 5 electrons. Okay, so 5 plus 5, that means you are having the 10 electron. That means you have to write the electronic configuration of the 10 electrons. So how you write the electronic configuration? Sigma 1s gyrate, it is having the 2 electrons. Then sigma 1s ungyrate, it is also having the 2 electron. Then you are having sigma 2s, it is also gyrate, so you write the 2 electrons. And then your sigma and debonding you have to put over there. So this is positive, this is 2s, this is ungyrate, it is also having the 2 electrons. And finally you are having pi 2px, it is ungyrate, that would be equal to pi 2py, this is also ungyrate. And you will put 1 electron here, 1 electron here. If you count the electron, 2 to 4 to 6 to 8 9 10. So this is the configuration. And you know, for this value is the +1, and for this the value is -1. If you calculate the lambda, that will give you the +1 and the -1, that is 0. And when it is 0, you can simply write the sigma for this one. Okay, and if you calculate the 2s plus 1, that is 2 multiplied by plus half, because both electrons are having the paired spin here, sorry, parallel spin here. Okay, that means +1, that will give you the 3. Okay, and you know, your electron is present in the ungyrate and your electron is present in the ungyrate, right? So this is also ungyrate, if I write. Okay, so if you go for the parity, then ungyrate multiplied by the ungyrate, that will give you the gyrate. So far you are getting sigma 3 G, and whenever your G is there, G subscript is there along with the sigma, you will put the positive over there. Okay, so the moment you will actually put the positive, and then you will find, okay, it is fine, this is looking the correct one, but this actually will give you the wrong result. Why it will give you the wrong result? See, this sigma is actually, right, this sigma is coming from this pi actually, right? So you have to think about this one, 2s plus 1. When 2s plus 1 equals to 3, then you have to put the negative. If it was actually 2s plus 1, then you will write the plus. So 2s plus 1, 3 is there, so you will write the minus over there. So this is the minus. This is the correct answer for this one. And if you put that, then what would be your answer? Your answer is actually this one. Okay, 3 sigma negative G. This is how you can write actually. Okay, so there is no problem in that. Now moving to the C, there is no see, these are the problems actually which has been asked in the CSIR net examination. And lastly, what we can do, we can check the last problem. Okay, and last problem actually, you can write the problem of GATE 2012. Choose the allowed transitions. Okay, so how you will allow the, or not transitions actually, transition. In the question itself it is given the transition. Okay, so if you know, so what you have given in the A, your sigma G plus 1, and electronic transition is happening from here to here, that is 0, and this is plus actually, right? So here you see the spin multiplicity is 1, spin multiplicity is 3, so it is spin forbidden. So this cannot be your answer. Okay, then go for the B. What is given here? Sigma G positive and 1, and next is sigma U negative and 3. So this actually, you see here, this is 1, this is 3, this is spin forbidden actually, right? You can clearly visible here, you can clearly see here. So this is again cross, you can cross. Okay, then the option C, it is given here, your sigma G with plus sign and 1 here, and the transition is happening from sigma U plus 1. Okay, so you see here guys, it is parity allowed, so you can write allowed here, and it is also spin allowed, so this is allowed, there is no problem in that. And if you calculate the lambda, that means 0 minus 0 equals to 0, and for sigma 0 0, this is also allowed. and positive to positive is also allowed. So this is looking the correct answer. And the last option which was there in the question was just like that, sigma g with positive and 1, and it is just like that, u 1 and negative. Okay, so there is no problem, it is spin allowed. There is no problem, it is parity allowed. It is no problem, it is quantum number lambda allowed. There is no problem in that, but positive to negative is not allowed. Okay, so wave function sign is not allowed, so this cannot be your answer. So correct answer is the option C. So these are the problems which has been asked in the previous year CSIR net as well as in the gate examinations. Okay, so I made the 2 lectures earlier, and this is the last lecture. I hope this will help you. Okay, so that's it for today, guys. Thank you very much.